Chapter 12, calculation of medications by age, body weight, and body surface area. Patients other than average adults may require special medication dosing. Children are not small adults, but rather a distinct population of individuals that exhibits different pharmacokinetics, which is medication absorption, distribution, metabolism, and excretion rates than adults. The growth and development of the child or the focus of the field of pediatrics significantly affects medication dosing. According to the FDA, pediatric stages include newborn, infant, child, and adolescent. Geriatric persons and persons with organ malfunctions also have differences in pharmacokinetics, requiring the special calculation of many drug dosages. Most individuals with renal or liver dysfunction require dose adjustments of medication. With toxic medications such as chemotherapeutics, even non-elderly adults with normal organ function may require the use of body surface area based on height and weight for drug calculations. Since many dosing recommendations are standardized average adult doses, doses for special populations must be altered to meet the patient's need according to age, body weight, body surface area, and overall physical conditions. Pediatric doses of medications may be ordered according to body weight or body mass. The most common method of calculation uses grams, milligrams, or micrograms of drug per kilogram of body weight. The order therefore appears as grams, milligrams, or micrograms per kilogram. With this in mind, the child must be weighed with each visit to the hospital or physician's office to be sure the correct amount of medication is ordered. If weight is measured in pounds, it must be converted to kilograms. The conversion factor is 2.2 pounds is equal to 1 kilogram. All right, let's do example 12.1. All right, for example 12.1, what is the weight of a 22-pound infant in kilograms? So we need to look at our conversion sheet. We have 1 kilogram equals 2.2 pounds. So 1 kilogram is equal to 2.2 pounds. And we have 22 pounds. How many kilogram is that? So we have 2.2x is equal to 1 times 22, which is just 22. And then we still have our 2.2x. We want to get x alone, so we have to get rid of that 2.2 by dividing each side by 2.2. So now we just have to take our 22 pounds and divide that by 2.2, which gives us 10 kilograms. An infant weighs 18 pounds, 4 ounces. What is an infant's weight in kilograms? If a person is weighed in pounds and ounces, the ounces must be converted to pounds first. So we're going to use that conversion factor that they gave us of 1 pound is equal to 16 ounces. And we have the 4 ounces from the infant's weight. How many pounds is that? So 16x is equal to 1 times 4, which is just 4. And we have that 16x. So we want to get rid of the 16 on the side, so we only have x, so we divide it. And then we also have to divide 4 divided by 16, which gives us 0.25 pounds. So now we can add that 0.25 pounds plus the 18 pounds. So essentially the patient weighs 18.25 pounds. Now we need to convert those pounds to kilograms. So remember our conversion factor of 1 kilogram equals 2.2 pounds. And then we just simply plug in those 18.25 pounds. How many kilograms? So we do 2.2x is equal to 1 times 18.25, which is just 18.25. We want to get x alone, so we have to divide each side by that 2.2. So 18.25 divided by 2.2, which is going to give us 8.29, so 8.3 kilograms. So example 12.3, a 53-pound child has been diagnosed with epilepsy. The physician orders Dilaate and 30 milligram capsules to be given at 2.5 milligrams per kilogram per dose. How many capsules should be given per dose? So I've already wrote the conversion factor up here to do, first we need to take care of those 53 pounds, get those to kilograms. That's our first step. So we have 2.2x is equal to 1 times 53, which is just 53. We need to divide both sides by 2.2. We get rid of the 2.2 on that side. Now we just have to do 53 divided by 2.2, which is going to give us like 24.09. So we'll say 24.1 kilograms. All right, and then the doctor wants it dosed at 2.5 milligrams per kilogram. So now we had to find out how much the patient can have based on their weight, which is 24.1 kilograms. How many milligrams can we give them? So we have 1x, which is just x, and then 2.5 times 24.1. So we get 60.25 milligrams. All right, then we have the capsules, which are just capsules. So we have 30 milligrams as 1 cap. And we need to give the patient 60.25. How many caps? Well, looking at this, so if we have a capsule that's 30 milligrams and we have to give them 60 milligrams, we're gonna just give them 2 capsules, right? If we do the math, that's what we would figure out, 30x. We would actually figure out 2 point something because we have that 0.25. We cannot give 0.25 of the capsule, so we would actually just have to round that down to 2 capsules per dose. So of course we have our example with a 42-pound child. So 1 kilogram is equal to 2.2 pounds. And we have 42 pounds. So we can do this proportion just like we've done for the other examples, but we can just, one little trick when it comes to the this problem is you can just take their weight and divide it by 2.2, which is in this case looks like 19.1. And then we can do our problem. So we have 20 milligrams per 1 kilogram for dosing. We need to give them 19.1 kilograms worth of medication. How many milligrams is that? So then we have 1x, which is just x, is equal to 20 times 19.1. So we'll do that in our calculator, 20 times 19.1, which gives us that they need 382 milligrams. We have the strength of the medication at 125 milligrams per 5 ml. We can plug in our 382 milligrams. How many ml is that? So we have 125x is equal to 382 times 5. Now we'll just do 382 times 5 first, which is 1910. All right, so now we have 125x equals 1910. We want to get rid of that 125, so we just have x on this side. So we need to divide both sides by 125. That crosses off. We just have x. And 1910 divided by 125 gives us 15.28 ml. Or we can round that up to 15.3. And we need to give this to the child every 8 hours. So we would just divide that by, to find out the dosing. So 24 divided by 8 is 3. So if we take we'll do 15.3 and divide that by 3. We get the answer of 5.1 ml per dose. Clark's rule is a method for approximating pediatric doses based on the manufacturer's recommended average adult dose by relating the child's body weight to an average adult's body weight. The assumption with the formula is that the average adult weighs about 150 pounds, which we know is probably not necessarily true now. Because studies of body weight of adults have shown that the average adult now weighs more than 150 pounds, Clark's rule is being phased out as a means for calculating pediatric doses. Technicians should still be aware of this method. So here's Clark's rule. The child's dose is equal to the child's weight in pounds over 150 times the adult dose. And an answer using Clark's rule is always an approximation. All right, let's do example 12.6. All right, so example 12.6, we're going to use the formula up here at the top. Clark's rule, the child's dose is equal to the child's weight in pounds over 150 times the adult dose. A physician orders Cefzil for a 38-pound child with an upper respiratory infection. The adult dose for Cefzil is 500 milligrams every 24 hours. Because the physician did not order an amount per kilogram of body weight, calculating this medication by milligrams per kilogram body weight method is not possible. So this one, we're going to use the formula. So I'm just going to go ahead and fill in. I'm going to use CD for the child's dose. The child's weight in pounds is 38 pounds over 150. And then that's going to be times the adult dose, which is 500 milligrams. So now in my calculator, I am simply going to do 38 divided by 150 times 500. Which gives me 126.66. We're going to round that to 126.7 milligrams. And then down here, if the prescription is filled with Cefzil 125 milligrams per 5 ml, how many milliliters will be needed per dose? So I'm just going to fill in the 125 milligrams over 5 ml. And then I'm going to plug in the 126.7 milligrams to figure out how many ml. Now, I want you to look at the strength of the medication, 125 milligrams per 5 ml. So that means every time the patient takes 5 ml, they're receiving 125 milligrams of medication. So we should know by now that 5 ml is 1 teaspoon. And that using these methods like Clark's rule and Young's rule and all that stuff, these are older formulas that we use that are based on approximations. Now we tend to use the milligram per kilogram body weight method more often. But before you do the calculations, I just want you to look at that. Since it's 125 milligrams per 5 ml, and we want to give the patient 126.7 milligrams. So that's only 1.7 milligrams more than what the strength is. So because we are approximating this, this simply is going to just be 5 ml, which is 1 teaspoon. And if you're like, okay, well, how did you just know that? Just go ahead and do the math. So 125x is equal to 126.7 times 5. Hopefully you can figure that out on your own and it'll come out to like 5.07 or something like that, which we would round down to 5 ml. Medications ordered based on an amount per square meter provide the most accurate determination of therapeutic doses because they are based on both body weight and height. This form of calculation is often used for pediatric patients, elderly persons, and when dosing toxic medications such as chemotherapeutics. BSA refers to the total body area that is exposed to the environment and is expressed in square meters. To calculate BSA in square meters, the weight and height of a person must be measured either in the metric or household system and applied to a nomogram, which is a chart which weight and height are plotted to determine the BSA. So this is a nomogram for measuring body surface area for a child. And then here we have for an adult. To use a nomogram, locate the patient's height and weight in the same measurement system on the correct indication lines of the chart. So here it depicts the use of the nomogram. The person is 41 inches tall and weighs 36 pounds. So we have the 41 inches tall, so the height, and then the 36 pounds plotted here. So the BSA is 0.68 meters squared. The pharmacy technician will rarely, if ever, have to use a nomogram, but once again, it is good to be familiar with the concept. They typically are used by a pharmacist or physician in a clinical hospital setting. All right, so let's do example 12.7. A physician orders the chemotherapeutic agent cytotoxin 50 milligrams per metered square per dose IV for an adult who's 55 inches tall and weighs 160 pounds. What dose should be given? First, we need to plot the BSA using the nomogram, 55 inches and 160 pounds. But the answer's already done that for us, so we don't need to do that. All right, so first we're gonna do is plug in the dosing, 60 milligrams over 1 metered square. And we have 1.75 metered square. How many milligrams? We don't need to do anything with the metered square, it's just basically a unit. So this 1x is just x, and then 50 times 1.75. So that gives us 87.5 milligrams. All right, next it asks if the medication is 200 milligrams per 10 ml. What is the volume of the dose? So we would do 200x is equal to 10 times 87.5. And we can get our calculator out and do 87.5 times 10 is 875. We need to get X alone, so we need to divide each side by that 200 to get rid of it on that side. And then we just need to do 875 divided by 200, which gives us 4.375. We'd say 4.38 ml. And it looks like the book rounded it to 4.4 ml. Example 12.8, we're using this formula up here at the top. The child's dose is equal to the child's BSA over 1.7 times the adult dose. So you're going to use the nomogram that's given in the book and locate it. But they've actually already given it to us in this problem. I don't think you should have to calculate any on your own. All right, so we're going to plug in our information. So CD for the child's dose. The BSA is 0.86. So then 1.7 times the adult dose of 500 milligrams. Get out our calculator.
Yes. What kind of complaint? A noise complaint.
So we get like 252.9. I would say 253 milligrams. And then down here it says what dose should be given if the available medication is 250 milligrams per 5 ml. So just like the previous problem, we really don't have to do any math because the dose is 250 milligrams over 5 ml, which we know is 1 teaspoon. And we have 253 milligrams that we need to give. So since we're using a approximate method to calculate the dose, we will just approximate it down to 250 milligrams, which is 5 ml. Calculating medication doses for pediatric patients based on age. Pediatric doses have also been estimated by using Freed's or Young's rule, which are based on the normal adult dose. These formulas will yield approximate answers and should not be used with medications that have a narrow therapeutic index. Age is no longer considered a valid criteria for determining pediatric dosing, but a technician should still be aware of the following formulas. So we have Freed's rule, which is used for infants up to 12 months. So we have the infant's dose is equal to the child's age in months over 150, and then multiply that by the adult dose. So let's do example 12.9. Example 12.9. We're using the formula above we just talked about. So a physician orders amoxicillin for a 6-month-old infant. The usual adult dose is 500 milligrams. How many milligrams should the infant receive per dose? So I'm going to do ID is equal to the age in months, which is 6 months over 150 times 500 milligrams.
No? Was that a no and a no?
So 20 milligrams. And if the medication is 50 milligrams over 1 ml, and then we plug in our 20 milligrams, how many ml? What is the dose to give to the patient? So we're going to do 50x is equal to 20 times 1, which is just 20. So we have 50x is equal to 20. We want to get x alone, so we're going to divide both sides by 50. That cancels out. I just have x. And then we have 20 divided by 50 for our answer, which is 0.4 ml. Young's rule is used to calculate medications for children 1 year of age to 12 years of age. So we have the child's dose is equal to the child's age in years divided by the child's age in years plus 12 times the adult dose. Now let's go ahead and do example 12.10. Example 12.10. A physician orders amoxicillin for a 5-year-old child. The adult dose is 500 milligram per dose. What dose would be given to a child? To the child, sorry. And we're going to use this formula here. The child's dose is equal to the child's age in years over the child's age in years plus 12 times the adult dose. So the CD is equal to child's age in years, which is 5 years, and then their age in years plus 12. Kind of went together. And we're going to multiply that by the adult dose, AD, which is 500 milligrams. Okay. All right, so now we can do our calculations. We're first going to take care of that. 5 over 5 plus 12 is 17. So I'm going to cross that out. That's now 17. So now I can do my math. 5 divided by 17 times 500, which is going to give me 147.06 milligrams. And if the medication is available in 400 milligrams over 5 ml, how many ml do we need to give? So 400x is equal to 147.06 times 5. So we're going to take care of that multiplication first, which is 735.3. And then we want to get x alone, so we need to divide both sides by 400. That crosses off over here. And then on our calculator, we're going to do 735.3 divided by 400, which is going to give us this 1.83, so 1.84 ml, which we would round to 1.8 ml. Certain populations require special dosing considerations. In all cases, the manufacturer's suggested dosage should be the guideline for the amount of medication that is administered. Highly toxic medications also require special calculations for safe and accurate doses. In most cases today, BSA is the basis for calculating children's doses and chemotherapeutic medications. In the past, children's doses were estimated from adult doses based on weight or age using Clark's, Young's, or Freed's rules. These methods are not common now. With other medications, the physician may write adult or children's dosages to be given on the basis of the amount of medication per body weight, which is milligrams per kilogram. And that is going to be the most often.